right, folks. Let's get started here. This session here is going to be talking about spanning tree. At some point, we'll detail exactly how spanning tree works. We'll talk about the different types of spanning tree. We'll go through some of the optimizations and things that you can do to kind of like enhance your topology and make it a little bit more robust against kind of like failures on your switch network. So let's go ahead and get started. First off, what is a spanning tree? Why are we trying to use spanning tree in the first place? And the easy response to that would be that spanning tree is meant for loop prevention, right? In a redundant topology, without spanning tree, you run the risk of routing loops. And the way that routing loops occur is assuming that all my switches in this diagram have no MAC address table, they haven't learned any MAC addresses dynamically. What would happen would be if I send a frame into my switch over here, and let's just say that my source MAC address in this particular case is A, okay? The first thing that your switch has to do when it's receiving any kind of information is that it needs to record the source MAC address on that incoming interface. So one of the things that happens here is that my switch will learn about my MAC address from this particular port. And then if I don't have an entry to get to a certain destination MAC address, what the switches are going to do is they will replicate that frame out all ports except for the port it originated from. So what typically happens here is I will send one port this way, and or one frame this way, and then I will also send another frame this way, okay? I'm going to color coordinates, and I'm just going to talk about the first frame in red first. Again, if I send that frame over, what would happen is this switch on the right-hand side would have to learn about that MAC address of my PCA, right? Again, assuming that my MAC address table has not been filled out, I'm going to replicate this frame out all ports except for the port it originated from. So now you get this switch over here learning about how to get to PCA from this port, right? And again, repeating the process again, my third switch receives a frame. And so if I don't know how to get to its destination, I'm going to forward all ports except for the port it originated from. So essentially, I can send the port this way to the destination, and I can send the frame this way to this switch on the lower left-hand side, right? Now, it did get to its destination, but that doesn't stop the frame from moving within our switch topology. So if I just continue on, this switch on the lower left will learn how to get to PCA from this port. I'm going to forward out all ports except for the port it originated from, so I'm going to send it this way, right? This switch is going to learn how to get to PCA from this particular port. And then I'm going to forward out all ports except for the port it originated from. So I'm going to send it back here. I'm going to send it over here. That gets sent here. This goes to its destination. It gets repeated over here. And eventually what you end up getting is you end up getting kind of like a broadcast storm moving in one direction, right? Moving over to kind of like the second frame, which is in blue. What's going to happen in this particular case is that the lower left-hand switch is going to learn how to get to PCA from this port. I replicate out all ports except for the port it originated from. So at some point, this lower right-hand switch learns how to get to PCA from this port. I send it to the destination. I also send it up here where this guy will learn how to get to PCA. I then send it back over to the original switch. He knows how to get to PCA from here. I replicate it back to the original source, and I repeat this process over and over again. Okay, now this is a true broadcast storm, okay? And not only is every single time that the switch is going to be processing a frame, it takes up CPU utilization, but if you take a look at the MAC address table, like for instance, just take a look at this guy, he is learning how to get to PCA from this port, and this port. So how confusing is that, right? It's very confusing. So in order to stop this broadcast storm and for information being learned from the switches to basically stop this from happening, what we use spanning tree for is we use it to basically logically block a particular port. It doesn't mean that that port's down. It doesn't mean that it's unusable, right? It's just the port is up and up. It's just logically spanning tree will not accept any data coming in on that port, and it will not send any data out of this port, okay? So that's the reason for using spanning tree. This is the best way for loop prevention, is to block a given port within your redundant topology, okay? Now, there's a couple of things about spanning tree that we need to realize though, okay? It was published in the IEEE 802.1d standard. This is a very old standard, okay? And I will detail exactly some of the behavior of spanning tree with 802.1d. It is not the best version of spanning tree, but it is kind of the default spanning tree version that's running on all of our switches, okay? It does provide a loop-free redundant network. The way that it does this is that every switch exchanges what we like to call a BPDU, okay? We call these things bridge protocol data units. In your BPDU, it looks like this guy right here, okay? What's essentially happening here is your bridge priority can be any value from 0 all the way up to 65,536, I believe, okay? So the default priority is usually about 32,768, typically. Okay, so it's right in the middle there between 0 and 65,536. The reason why I'm mentioning this to you is because when we exchange our BPDUs, the idea is that I'm trying to become the best switch on my topology here, within my switch topology. The way that I determine who the better switch is going to be is this bridge priority, right? And typically speaking, in a switched fashion, the lower the number, the better it is, okay? So the higher the number, the less prioritized you are. The lower that you are, the better prioritized you're going to be on the network, okay? And we also exchange our MAC address information as well. This will matter here in just a minute, as soon as I flip the slide here. But yeah, we exchange these BPDUs every 2 seconds out. Every single port on the switch that's participating in spanning tree. And what we're really trying to do is just exchange informations with other switches is all, okay? So that's kind of the idea here. The reason why the bridge priority is from 0 to 65,000, because this is really a 16-bit number, okay? So when we look at the bit fields and all that, it's about a 60-bit number for your bridge priority field. So moving on. This is arguably the most important slide of our entire discussion here. And that is what spanning tree is trying to accomplish, okay? And for us, how do we determine what status our switches are going to become? So we have to define a lot of things here, okay? You guys can ask questions if you guys have them, so please. The first thing is this. Is that the root bridge is the most important switch on your switch topology, okay? Because basically what's happening is if you are the root bridge, most traffic is trying to converge to the root bridge, if that makes any sense. So what's going to happen here is all of our switches are going to compete against each other to become this guy, okay? So in order to become the root bridge, one of the things that has to happen is we have to exchange the BPDUs, and via the BPDUs, we got to figure out who has the best, I guess like a bridge priority and or MAC address combination, okay? So everybody wants to become the root bridge. And the reason for that, again, most traffic gets directed to the root bridge, okay? So that's really what's happening here. We will select one root bridge within a looped topology, okay? All other switches that are participating in spanning tree, they become what we like to call a non-root bridge, okay? So you're either the root bridge or you're not the root bridge, okay? Then after we figure out what your role is, each bridge has to then designate a port as a designated port or a root port. I'll talk about that in the next slide, I promise, okay? And then what happens whenever there's some port transition? So again, we'll talk about that a little bit later. But these are the two most important things I want you guys to, well, three most important things I want you guys to think of right now. We elect one root bridge, all other switches are going to be non-root bridges, and then they have to start electing certain ports to do certain things. You could be forwarding port, you could be an alternate blocking port, where if I'm a blocking port, right, that would kind of be like in that original example that I showed you, what spanning tree is trying to do, right, is block a port logically. So anyway, I like to think of this. This is the way that you guys should be thinking about spanning tree all the time, okay? Because this is what goes through my mind when I figure out which switch is which and what ports are gonna transition to specific states that I want, okay? So the first two things that I want you guys to think about is the bridge priority and MAC address. When spanning tree gives its BPDUs every 2 seconds to all the switches, we care about these parameters within the BPDUs. And these parameters alone will define exactly what your root bridge is going to be, okay? So I'm going to go to this next slide. I'm going to show you kind of like how I have configured this, okay? Now, just based on the picture here, we should be able to know which person becomes the root bridge. Because in my last slide, we take a look at the bridge priority. Whoever has the lowest bridge priority will become my root bridge. End of story, okay? So if you have a topology like this, what ends up happening here is I have a distribution A switch, I got a distribution B switch, then I got some access C and access D switches here towards the bottom, okay? Based on the priorities, I know that the lowest priority here happens to be distribution B because I've set the priority to be a lower number than everybody else on this particular network, okay? 24,000 is lower than 28,000, and that's lower than the default 32,000 that my access layer switches have. So in this case, this will become the root bridge, okay? Now, here's the thing though. A lot of the times inside of spanning tree topologies, people don't control this based on priority. They just kind of install the switches, they turn them on, and spanning tree just kind of works, right? But what would happen by default is if this person happened to have a priority of 32,768, and this person also had a default priority of 32,768, what happens now is because we all have the same priority, we must then look at the MAC address. That's actually what the second option is for spanning tree calculation, okay? So in this case, the person with the lowest MAC address would become the root bridge instead. In this case, that would be distribution A because their MAC address starts with a 1111, okay? This starts with a 2222, this is 3333, this is 6666, okay? So we know that the root bridge is going to be distribution A in this particular scenario, okay? But again, most of the time as an administrator, you're going to want to control who becomes the root bridge because all traffic will flow through the root bridge. It doesn't make any sense to make an access layer switch a root bridge because remember, you want to send all traffic to go through this root bridge, right? So if you incorrectly have a root bridge selection, what may happen is you may get, suboptimal switching, right? It doesn't really affect any users that are here on access switch D because whenever I send traffic, I'm going to send it to the root bridge anyway. And then from here, I can send it either here or I can send it either here, okay? No problems. Your problem is when this becomes the root bridge and then you have users over here on access C switch. Again, all traffic has to go through the root bridge. So I may have to send my traffic this way to go out, okay? Or I may have to send traffic up to this switch to go down and then come back up here to go out of my network. And again, that's suboptimal switching. But you would never know that unless you understand spanning tree. So this root bridge selection is very important, right? We want to be able to say, you know what? There could be 3 levels of your network, right? There could be an access level. There could be a distribution level. And then there could be another top level up here, and that top level could be your core, right? The idea with the switching environment is we want to allow the root bridge to become, at least on our distribution or distribution collapse core layer switching, right? So that we control the flow of traffic to move up our hierarchy of our topology, okay? So that's really why we want these switches in the distribution layer to become our root bridge here, all right? Now, half of this is already done. Okay, as soon as you know who the root bridge is, half of your thinking is done. You basically are finished with most of it, right? You only have to figure out what the other non-root bridges are going to do. So I'm going to go back on this slide here, and I'm going to show you the two other things you're going to look for if you are a non-root bridge. And basically what we care about here is we care about cost and we care about port priority, okay? Cost, what is that? Is that a dollar amount? What is it, right? In the definition within a switch topology here, cost does not equal the amount of money that you paid for a particular link. It doesn't matter how much that link cost, right? It doesn't matter how much money you spent on the switch. Cost is an arbitrary metric that has a relationship to bandwidth, okay? Here is a bandwidth cost association that I always show to my students here, right? Let's say you have a 10 megabit link, okay? That artificial cost may be 100, okay? If you have a 100 megabit link, that cost could be 19. If you have a 1 gigabit link, then I guess that could be a cost of 4. And then if you have like a 10 gig link, that could be a cost of 2. And for instance, a 20 gig link on a LAN segment, okay, that would be equal to 1. So we start to see this relationship with spanning tree in that the higher the bandwidth is, the lower the cost is, the better the link. The lower the bandwidth, the higher the cost, the worse the link is going to be. And again, in spanning tree, it's kind of easy to remember. Remember, who becomes the root bridge because of what? The lower bridge priority, right? If the bridge priority for all switches are the same, then I'm going to move down one notch and I'm going to take a look at the second kind of stipulation. And this would be your MAC address. Typically, the lower the MAC address, the better, the switch. And same thing goes with cost. Your cost here is the lower the number, the better you are, okay? So in those terms, because I know who the root bridge is over here, for all my non-root bridges, I'm going to calculate the fastest way back to the root bridge, okay? If you take a look at distribution A over here, okay, what's a better path for me? Is it this path, which is a cost of 2? Or maybe if I go down this path, that's going to be 4, and then I have to go out this path, that's another 4, that equals 8. Okay, what's better, 2 or 8? Definitely 2, right? Or I might think of it this way. What if I send the packet down this way? That's 4, and then once it gets down to this switch, I have to send it back up here to the root bridge. That would cost another 4. So in this case, that would also be equal to 8. But again, we know what the best path is going to be in this particular case. That best path is going to be this port, okay, to go back to my root bridge. And what we end up calling this port is we call this port a root port. By definition, a switch will only have one root port because only one best way to get back to the, to the root bridge, right? So we call that port a root port, okay? Effectively, this port is in the forwarding state, if you will, okay? So that's all that's going to mean. And all your other switches are also going to perform this calculation, right? Well, is it better for me to go this way or is it better for me to go this way, right? If I go this way, this is going to be 4. If I go this way, that's 4 plus 2 equals 6. So I know that basically that's not going to work. I know that this is going to be the best port here for me. And this is going to be my root port here. Fastest way back to the root bridge. Okay? Same thing for access D switch. They will make their own decision to say, well, I can send the packet this way, which will cost 4, or I can send it this way, which will cost 4 plus 2 equals 6. So which one's better? I definitely know that the port that I'm going to be selecting is going to be this port, and this becomes the root port. Okay? Every non-root bridge will have one root port only, okay, on a switch topology. Okay, fastest way back to the root bridge. And once this happens, okay, I guess there is one little thing that I want to talk about. What happens then when I'm on the perspective of switch D over here, but I have 2 links? So I could go this way. That would cost me 6, right? And then I could use this port, which is 4, but I could also use this port, which is a gigabit port. That would also equal 4. So in this particular case, the cost is the same. Is there a tiebreaker? Absolutely, right? Your tiebreaker in this case would be your port priority, okay? And the way that port priority works is kind of janky. It's kind of weird. Let's pretend that this is fast Ethernet 0/10. And let's just say that blue port that I just barely created here, let's just call that FA0/24, okay? The way that Cisco calculates port priority is literally the port number that you have. So for instance, the port priority for FA010 could be a port priority that would be equal to 128.10. And the port priority for fast Ethernet 024 would be 128.24. And of course, if you use like virtual interfaces, or if you use like, you know, I don't know, like, what is it? If you use virtual interfaces, or if you bundle your ports together via port channels, those numbers are going to be kind of going, they are going to change a little bit. But generally speaking, the lower the port number, the better you are. So in this particular case, this would become the root port, okay? And then this port would be in the blocking state, if that were the case, okay? So again, we only have to remember 4 things to kind of figure out our switch topology here. And I want you guys to separate this in 2 different parts, right? The first part, bridge priority and MAC address, will automatically determine who the root bridge is, okay? For all non-root bridges, they have to calculate the best path back to the root bridge to define a root port, okay? If you are a root bridge, like you are here, let's call this root, I'm going to write this out. If you are the root bridge here, you will not have any root ports on this particular switch, because you are the root bridge. There is no port to get back to the root bridge, because you are the root bridge in this particular case, okay? So you only see root ports on non-root bridges, okay? Root port here, and root port here, okay? Any questions so far? Okay. I guess this is where things kind of get really confusing for most people. Ben, how do I figure out which port is going to be in the blocking state, right? Well, to figure out who is going to be in the blocking state, you need to kind of look at your loop topology and ask yourself, where do I find a loop? So in this particular case, let me show you guys where there are 2 loops in this particular topology. Can you guys see that there is a loop here? And can you also see that there is another loop here? So there's 2 effective loops in this particular topology, okay? And the way that it works is I'm going to look at the blue topology first, the one that I outline in blue, okay? So when I take a look at that, I'm only looking at distribution A switch, distribution B switch, and access layer D switch, okay? So here's my question to you guys. Out of distribution A, distribution B, and access D, which switch has the worst credentials as far as priority and MAC address goes? it's probably going to be your access level D switch, right? Notice his priority is highest. It is 32,768 at this point in time, right? Then you have 28,672. Then you got 24,576. So because the priority on access D is the worst out of the bunch because it's the highest number, that means that this switch will have a blocking port on this particular topology. So the port that I'm going to be blocking in this case is this right here, okay? And that's purely based on the fact that I am the worst switch within this loop topology, okay? Typically the worst switch is the one to have the blocking port. Once we have figured that out, okay, I guess we can take a look at the second topology here. In the second topology, we know that we are looping in this fashion. So out of these three switches of distribution A, distribution B, and access C switch, again, who has the worst priority MAC address combination? 32,768, I got 28,000 up here, I got 24,000 over here. It looks like access C switch is the worst. So what ends up happening is I'm going to be blocking this port on this particular switch, okay? And you know what? Once you figure out who your root bridge is and where your block ports are, you're basically done with your spanning tree configuration, right? Because you figured out what your pathing is going to be. If I have any kind of data that's coming from my access level switches, because you know you have a lot of endpoints connecting to the switch here, if anybody tries to send you frames, you know exactly where you're supposed to go. You're going to receive that incoming frame, and where you're going to send that is you're going to send it through the root port, right? The fastest way back to the root bridge. So I'm going to send it out this port right here. And I will never use that blocked port that's going adjacent to the distribution A switch, okay? Same thing goes with my access C switch. I have a bunch of users that are connecting here. When they send traffic inbound on access C switch, again, I'm just going to follow my root port to get back to my root bridge. That's what we're trying to control. So I'm going to send all of my traffic in this gigabit link that goes diagonal to distribution B. Question? Someone unmute out there? Okay. Well, that's kind of the gist of spanning tree, right? And that's the thing about learning spanning tree is once we figure out who the root bridge is, or we can control who becomes the root bridge, then it's just kind of figuring out where all your block ports are. And you as an administrator, you can be able to control these things, right? You can control exactly who's the root bridge, who's going to have the blocking ports, just by modifying the priority of all your switches. That's what most students have to understand when they're dealing with spanning tree.
I got a question.
Sure. Go ahead. Ask your question.
BPTU guard?
Yes, we will talk about. Yeah. Hold off on BPDU guard until we'll probably get there in about 10 minutes. But I'll talk about BPDU guard. I'll talk about BPDU filter, and then I'll also talk about port fast and how that kind of affects our topology. Okay. I promise it's coming. Yep. Those are going to be at the very, very end. Okay. All right. Any questions to how spanning tree kind of works here, other than the BPDU question? Okay. To be able to understand spanning tree, what we need to do here is I use one command, right? I use the show spanning tree command to basically show me exactly what it is that I'm trying to see here. And because to be honest with you guys, right? When you first look at a topology, a switch topology, and you're like, I don't know what I'm looking for, right? That's what most people think when they're seeing this topology. What you're trying to do is figure out who the root bridge is. So in a regular topology, when you look at it like this, you may not know because you might not know what the priority or MAC address is for every switch. So in the real world, you know, it's a crapshoot, right? If you log in here and you do that show spanning tree command and it's not the root bridge, well, then try your luck somewhere else. If you go here and it's not the root bridge, try your luck somewhere else. When you have found your root bridge, half of your work has already been completed, okay? And this command is kind of what you're gonna do to all 4 of your switches. When you log in, you're gonna do a show spanning tree command. And basically, on the show spanning tree command, it tells you what version of spanning tree you're running. More on that in a little bit, okay? But it tells you a couple of things here. It tells me about my root ID, which always tells me about who my root bridge is. So it does not matter where you go within the topology to do the show spanning tree. Every switch should have the same parameters here, okay? So the root ID always tells you about your root bridge, folks, regardless of where you're at. So let's say this was my root bridge. If you go here, and you go here, and you go here, and you do a show spanning tree command, all 4 of these switches that you log into, they will essentially show you the root ID and the MAC address and exactly how to get to the root bridge, okay? The only caveat is this, okay? Notice that root ID. If you're not the root bridge, it will tell you exactly which port you are going to have to use to get to that root bridge. So we call this our root port. When you take a look at this, isn't that the same interface that's here with Ethernet 00? Of course it is. That is the root for the role. You see that? So if you're not the root bridge, at least it tells you, okay, well, you're not the root bridge. Here's the root bridge's priority and MAC address, but you're going to use your local port here to be able to get to that root bridge at some point in time, okay? The caveat is when you are the root bridge, the system tells you that you are the root bridge. So if you lucked out and you just did a show spanning tree and you see this image here, where you see that the bridge is the root, then you basically already have your topology planned out. You know who the master It always tells you about your root bridge, even if you are the root bridge, okay? Your local switch, okay? This is going to be the switch that you are currently on. So if I'm switch 3 and I do a show spanning tree, my switch 3 has this priority and this MAC address, okay? And you know what? I happen to be the root bridge. That's why the priority and MAC address here are exactly the same, right? And that is because I am the root bridge and my bridge ID tells me about myself, okay? When you go to another switch that is not the root bridge, notice show spanning dash tree, and you look at the root ID. It doesn't tell you it's a root bridge. So you'll notice that the priority here for the root bridge and the MAC address are different than the priority here on your local switch, okay? So when you look at that bridge ID here, notice the priorities are two different numbers. One's 24,577, another one is 28,673, okay? So if those two numbers are different, it means you're not on the root bridge. But it's okay, you can use this port because this is going to be your root port to be able to trace yourself back to the root bridge. And that's what I tell my students all the time whenever I teach this course is, again, when you look at your topology, you might not know who the root bridge is. So the fact that I log in here and I do that show spanning dash tree command, okay? If I do a show spanning dash tree command here and it says that this is my root bridge, then that means if you want to look at your spanning tree topology more or you need to follow your topology somewhere, this is a hint that you should follow your root bridge. So whatever this port is connecting to, you're probably going to want to telnet here second or SSH, whatever you do, and then you're going to repeat that show spanning tree command again, okay? And it should then tell you, oh yeah, this guy's the root bridge. As soon as you know that he's the root bridge, make sure you calculate for all other non-root bridges for their root ports, okay? So I guess that's kind of the big idea with spanning tree is you need to understand these show commands, right? This is the most important show command to kind of understand in spanning tree. So, and then let's show you another one just to show you how different this can be. Notice This is going to be the third show command that I'm going to show you guys. Notice I'm not the root bridge because this is telling me how to get to, this is my root port to get back to the root bridge here, right? Here is my local stuff. I have local priority and I got a local MAC address here. And here is my root bridge. Oh, I did that wrong. I'm sorry, guys. So notice right here, you have your root port here. You got your priority right here. This is what I wanted to show you guys. I have a root port in Ethernet 02 that kind of coincides here, but I also have a port here that's in the alternate blocking state. Notice the state here is that I'm blocking this particular port. Okay, and it looks like I'm blocking that port on Ethernet 01 in this particular case. Okay, so whenever you do a show spanning tree on a switch that is effectively blocking, that's kind of what you're looking for. Okay, again, with spanning tree, you're just trying to figure out what your switches are trying to do here, right? Alternate blocking, root port. Okay.
Someone's at doorbell.
Sorry about that, guys. You also have this over here. You have blocking here, you got root forwarding here, right? You got root here for the root port, and then this is your root bridge, okay? And you'll notice that some switches, like for instance, the root bridge, okay, if this was in fact your root bridge, they will never have a blocking port on the root bridge ever. The only thing that you'll ever see is you'll see that these ports are marked as designated. And designated ports are effectively forwarding, okay? Forwarding here, okay? And notice distribution A is not a root bridge, but you'll notice that this will also be designated forwarding, and that this will also be designated forwarding, okay? So that's kind of what we're trying to do, is figure out what each port is doing on our network. But once you figure that out, you have figured out spanning tree, okay? Anyway, let me get past all of these little show spanning tree commands. Those are the ones that I like to kind of, figure out exactly where my traffic flow is moving. And remember, it's always going to move up to the root port. That's the way that we're steering all of our frames, okay? I took this from the CCNA class, but there are different versions of spanning tree. I know sometimes it can get very confusing, okay? But this is a very good table to just basically show you guys the differences of each spanning tree, okay? And I guess
I got a question.
Go ahead. Question. Go ahead.
Did you already talk about span tree port pass?
I have not. I'm going to talk about that here in just a minute. Okay, we're almost there,
okay,
folks. Okay.
All right.
Yeah, the versions of spanning tree here that we have here, we have regular spanning tree with 802.1d specification. Okay, it is slow as far as convergence goes, and it doesn't use up a lot of CPU resources, right? And notice the number of trees. This is the most important differentiation between the different versions of spanning tree, is that this has one tree, okay? Which means it has one instance of spanning tree running for your entire network, okay? Cisco, because Cisco comes out with their Catalyst switches and whatnot, they have their own version of spanning tree, which is actually based off of 802.1d specification, okay? The only difference here between Cisco's specification and the 802.1d specification is that Cisco is going to create a separate instance for every VLAN that you got created on your network. So if you have 100 VLANs that are active on your network, that means that you have 100 spanning tree instances. And when you think about having 100 spanning tree instances, right, that's kind of sucky, because if I have 100 VLANs here, that means that every 2 seconds, I am sending a BPDU for every single VLAN every 2 seconds. So that means that I'm sending a BPDU for VLAN 1, and I'm sending a BPDU for VLAN 2, and I'm also sending a BPDU for VLAN 3, and so on and so forth until you get to VLAN 100. And you're going to do that for this port as well. And everybody else is going to start exchanging BPDUs. 100 BPDUs every 2 seconds for every VLAN. So that is Cisco's enhancement. I know it doesn't sound like an enhancement now, but it is kind of an enhancement, okay? It is still slow. How slow? About 30 seconds as far as convergence goes, okay? 30 to 50 seconds, okay? And that's too slow, to be totally honest, okay? Why is it that Cisco created one instance for every VLAN, right? The idea with Cisco is they decided to do something like this. They decided to say, you know what, let's do some load balancing, right? So in this particular case, I may be the root for VLANs 1, 3, and 5 here. So that means that I'm going to probably block this port. This is going to be my root port. This is probably going to be my root port. I'm probably going to block here. So you can see where the traffic is flowing in this particular picture, right? But in Cisco's enhancement, because you have different versions of spanning or different instances of spanning tree running, it is possible for you to go over here and make this person the root for VLANs, let's say 2, 4, and 6. And when you think about this guy becoming the root bridge for VLANs 2, 4, and 6, that drastically changes everything. Because this then becomes the root port for that particular switch. And then I may be blocking on this port. And when you look at access D switch, this may be the root port for that VLAN 2, 4, and 6, but then I also block over here for that port. So as you guys can see, what happens here is we will control traffic to go out our network this way. Hence the load balancing scenario. Okay, so Cisco is the first one to kind of introduce this load balancing thing. But the problem with Cisco is that for every VLAN you created, that's a separate instance, right? That may be overkill, okay? Especially for larger environments that have hundreds of VLANs that are active at a given time, right? So because of that, that kind of makes Cisco's enhancement really, really bad for CPU utilization, right? Especially if you have a lot of VLANs. So just be very careful on a Cisco switch, okay? What then happened is the 802.1d specification was upgraded to 802.1w. This is rapid spanning tree. The difference here is that the convergence changed from 30 to 50 seconds, okay? And 30 to 50 seconds here. That changed to about 2 to 3 seconds as far as convergence goes. So it was super quicker, links come up faster, but you have to enable this. Right? It is not the default spanning tree version that's running, okay? This is the default spanning tree running. Or if you're on a Cisco device, I guess it's PVST+, okay? So again, this is a spanning tree version that we do have to turn on. But at the end of the day, you still have one instance for your entire, for your entire network. So that's the thing is you can't load balance with RSTP with 802.1w, okay? Then came Cisco's enhancement. Cisco said, you know what? We're going to pat ourselves on the back as well. We're going to create rapid PVST+, right? Rapid convergence time's better with 2 to 3 seconds. And I can also load balance, right? I can load balance here because I can have different instances running at a time. So that's the benefit. I'd say the best version of spanning tree running is probably multiple spanning tree because it is based off of rapid spanning tree. Okay, so it is quick. But here's the thing about multiple spanning tree, you, the administrator, you're creating these instances. So for instance, I could create instance 1, and then instance 1 could contain VLANs 1 through 10. Whereas I could do this, I can say, you know what, I want to create instance number 2 here. And then what would happen is I would create VLANs 11 through 20 and add them into that instance. And in this particular case, I only have to send BPDUs for these 2 different instances. I don't necessarily have to send 20 BPDUs every 2 seconds out every single switch port. So this is better on CPU processing. It's fast, but it just does require a bit more configuration is all. But that's kind of the differences of the different spanning tree versions that you're running here. Again, I think this one is probably the best one for enterprise switching and routing. But again, up to you what you guys are doing there. Okay, it is not the default though. The default is going to be either this guy or this guy for a Cisco device. Okay.
I have a question.
Yes.
So when you're talking about multiple instances, can you have multiple instances on one device, or that's spread out to multiple devices?
Multiple instances on, yes, so you're creating multiple instances on a switch. Yes.
Switch.
And that will communicate to other switches that are connected to. You're hoping that you would set up the instances correctly on all of your switches, right?
Mm-hmm.
So, yeah.
And so then the other question is regarding once you start setting up your priorities, you specify your range of VLANs that you want to prioritize per device. Where does the native VLAN fit in there? That's one of the things I notice on my current deployment is my native VLAN. I set up my root device to be my gateway, and I haven't included my native VLAN, and I feel like that's one of the causes that I'm seeing some loops on my deployment. It's because of the native VLAN. Somehow the native VLAN, it's in a totally different switch.
Correct. And let me talk about that here too, because realistically, if you're going to be changing the route priorities and whatnot and changing the load balancing scenario, what you're going to be doing is you're going to be using these commands here to set the priorities.
Right.
Okay. There's a couple of different ways you can go about doing this. Okay. One way of doing this is, and your native VLAN example that you were talking about, let's just assume native VLAN for this discussion. Let's just assume it's native VLAN 1, okay, because that's the default. So what would have to happen is if you're going to individually specify which VLANs are going to have which priority for whichever MAC addresses, notice what you're doing here on distribution A, right? In distribution A, I'm saying spanning dash tree VLAN X. And if you want to specify your particular route bridge for VLAN 1, you're going to say 1 right here. And that would specify your native VLAN 1. And then you could say route primary. What primary does is it gives you this priority here, 24,576. Whereas if you go over and you configure something like this, where you say route VLAN 1 route secondary, that will automatically change that priority to become 28,672. So that's the thing is when you configure this individually, you're probably going to, like, let's say you do this for VLAN 1 and then you want to make it primary, that would make this guy the route bridge for VLAN 1. Okay?
Correct.
Yeah, and then you would have to do that for every other individual VLAN. It's different for multiple spanning tree because instead of saying VLAN 1, you specify your instance instead of the VLAN 1. You see that?
Okay. And then, so definitely when you were talking about multiple instances and separating VLANs and the way to converge, would that be a good scenario? I mean, a good scenario right here I have, let's see, 10, 20, 30 VLANs on a specific site.
Okay.
And then when it comes to separating instances, the way I have them, it's, my lower priority, let's say 60 to 70, it's my administrative VLANs, including my access devices, 800 to 8010, it's my voice traffic, and then 900 to 910, that's my wireless traffic. So can I create instances based on those scenarios?
Most definitely. I would do this if I were you. I would create, and it depends how complicated your topology is. I would create instance 1 for things like data, okay? And then what you could do is you could, and data could mean a lot of things. Data could mean like transactional traffic, business to business traffic, could be voice, could be video, however you want to define that, right? Then I would think about doing things like instance 2. And in instance 2, you might want to put things like management stuff here, right? You might want to put things like native VLAN stuff here. Wherever your native VLAN is, put it on the second instance. Or whatever is going to be for things like maybe you have multicast traffic that you want to control, right? You could also put multicast traffic here. So that's the thing that I typically do is I like to separate my instances, one for data, right? Voice, video, data, whatever that might be. And then I can implement QoS on those links. And then the other instance would be for management, native VLAN stuff, multicasting and things like that. So.
Okay.
Thank
you.
But you gotta remember, right? If you create multiple instances, you will have to go to each switch and create the same instance on every single switch and make sure that your information is correct on every switch, right? Because it doesn't do you any good if your instance 1 on distribution A doesn't match up with distribution B's information for their instances. Does that make sense?
Interesting. Yeah. Okay.
Yeah. There was a comment. Yeah, go ahead.
So when you talk about instances, you're talking about VLANs, right? Voice,
right.
data.
Well, in the what's basically happening is if you do MSTP, what you're doing is you're giving the priority to the instance, not the particular VLAN, if you will. Okay. But that's what we were talking about is just MSTP. Yeah, we were talking about that because of the instance kind of thing, right?
Okay. Yeah, I get you.
Yeah. But in any of these spanning tree versions, you most definitely, you can just use what I was specifying here. You could just specify whatever VLAN number you want and then root primary or root secondary. Okay, and that would then change the number to either be 24,000 for primary, 28,000 for about the secondary command. Okay. And then there's also another thing too. You could, if you didn't want to do this, you could say VLAN X, whatever VLAN it is, and you could say priority, and then you could specify any priority from 0 to 65,536. Again, the lower the number, the better you are. So some people that I've seen do this is they're saying, hey, you want this to become the root bridge? Make this 0. Okay, that will guarantee that will become the root bridge hands down, right? So, but just realize that you need to understand the default. The default is always 32,768. And then like for Cisco devices, it's really 32,768 plus whatever VLAN number you are. So if you're VLAN 10, that number actually becomes like 32,778 or something if you're looking at VLAN 10, right? That's kind of the way that Cisco gets away with having a separate instance for each VLAN, is that the priority and VLAN ID are mixed into that. But again, generally the lower the number, the better you are, okay? So some people just use the command and then, yeah, end of story, right?
That goes for the root ID as well?
I'm not sure about the root. I don't think I've ever used the root ID. Is that something that you can define in standard?
Automatically generate.
Okay, yes, yeah, the root ID would be the priority, right? So, but remember, the root ID here just tells you about this thing, right? It tells you about the priority MAC address, cost associated. It just tells you about the root bridge is the idea. So if you want to control who the root bridge is, it's technically the priority command, okay?
Gotcha, yep.
All righty. So that's kind of how you would do load balancing, right? Make this guy root for, 2, 4, 6, like I mentioned before, and then make this other guy over here root for 1, 3, and 5, whatever you want. But again, you're going to have to control this for every single switch, right? And honestly, you only have to do this on your distribution layer switches, right? You really don't have to touch your access level switches, just leave them to the defaults, okay? They can make that decision on their own. We want to control who becomes the root bridge here, so.
That's just to clarify. That's not the case for if you're doing multiple instances, right?
Yes, in multiple, then you would have to specify the instance instead of the individual VLAN, right?
Even for your access switches, or no?
For your access switches, yeah, for your access switches, you can put instances in there. Even if you don't put the instances, you got to remember that, again, even if you don't put instances here, these guys are going to start sending BPDUs anyway. Yeah. So as long as you're controlling it up here, your bottom switches will still work with the system, if that makes sense.
Okay. Yeah, that's what I was kind of confused. Okay, I can definitely configure it if you have two distribution boxes, but
sure.
I have one, my root, my gateway, and then I have the switches on the bottom. So if I create multiple instances, it will have to be, I can just create it on the distribution side.
Exactly. You don't have to do it everywhere. That is preferred here. Just do it on the distribution and you're good to go.
Perfect.
Okay.
Thank you.
Cool. Alrighty, folks. Last slide here. And this is kind of like the slide where most of you guys kind of jumped in to kind of talk about these features, right? Some of the enhancements here is port fast, BPDU guard. What the heck does BPDU filter actually do? Okay. A couple of things that I want to mention to you guys. These enhancements are typically not for your distribution layer. Okay, do not think of ever doing either port fast, BPDU guard, or BPDU filter on your distribution layer switches. There's no need for it, okay? The idea here is that these commands are meant solely for your access level switches, the switches that are going to be connected to the endpoints, right? And the idea here is this. Let's talk first about port fast, okay? What is port fast? Like, what does it do for me? If I have users that are connecting to this switch over here, the fact of the matter is this. When we're thinking about the older spanning tree versions, okay? Oh, and again, take this with a grain of salt. The older spanning tree versions have a default timer of how they can switch their ports from blocking to listening, to forwarding to, you know, root port forwarding or designated forwarding, right? It could take anywhere from 30 to 50 seconds to transition that port, okay? So that's kind of the idea here, is that if this is decided to be a blocking port here, if my root bridge goes down, I need to change this so that this goes up, so that I can start forwarding out to my secondary root bridge that's going to be handling all of my traffic. But that could take 30 to 50 seconds for convergence, okay? The idea is this. Even if the root bridge goes down, should your switch calculate this port? Because if you don't set port fast, this port is technically part of your spanning tree operation, okay? Which means that whenever there's a change on the network, that port could transition from listening to learning, from learning to forwarding, and that could take 30 seconds to just tell this port that it can finally forward again, okay? What we're trying to do with spanning tree port fast is this. We are trying to make these ports that are connecting to our endpoints as designated forwarding. That way, whenever there are changes on your network, like when your root bridge craps out on you, that your switches aren't going to these ports that are connecting to endpoints to say, oh yeah, I got to calculate this, I got to suspend all traffic, I got to listen, I got to learn, and I got to go into forwarding state. You don't want that. So in this case, we make these ports that are pointing to endpoints designated forwarding by placing port fast on them, okay? There's two ways that you can set a port for port fast. One is on access C. Notice how I have a configuration, but this configuration here, notice this is under config IF. This is under the actual interface configuration. If you were to ask me, I prefer this, okay? The other way to do it, the second way to do it, which would be if you look over here in access D, notice where I'm at here. I'm under here, under the config, which means I'm under the global configuration. And that just basically means that with the spanning tree port fast default command, that means that any port that is in the access state automatically has the port fast command applied to it. But this is why I don't like the second configuration, because it will work, but here's why I don't like the second configuration, okay? Let's say you do that. And let's say that this guy's connecting to a PC here, okay? Let's say you haven't configured advanced switch security. So you didn't configure things like 802.1x port-based authentication. You didn't turn off things like dynamic trunking protocol. So if this was an attacking PC and they wanted to attack your network, you know what they're going to do? Let's just say they send a DTP frame, dynamic trunking protocol frame, and they say, hey, I want to trunk with you, okay? If this happens and you did not turn off DTP, what would happen is this would then turn into a trunk. If that turns into a trunk, you kiss this command goodbye, because now that this is a trunk, it is no longer an access port. If it's no longer an access port, it's not going to be in the port fast mode anymore. So these can be dynamically negotiated to have a trunk configured, and then it would get rid of your port fast command. If you do
Wait a
Go
second.
ahead.
So you're saying that when you plug in a PC, like most switch ports are access ports.
Yep.
Are you saying?
And again, this is just assuming that this was not configured. You know how you can by default, you don't really configure these ports to be access. You could. You have three options, right? You can make it access, or you can make it trunk. But if you don't specify access here, then this is going to have DTP taking over. Okay.
Okay.
Which
I didn't know that.
Which in this case, right, I don't want them to, because if you connect two switches together, what's going to happen? They're going to trunk automatically, right? That's what DTP does. So if you haven't protected yourself and you didn't, let's say you forgot to put access mode, or you forgot to turn off DTP by saying switch port non-negotiate is the way that you turn off DTP. So I do switch non as a short version of that, but that will turn off DTP. But that's the thing is, in some environments, right, I've looked into switches and they don't actually say switch port mode access, even though that's what they're doing. So that's the thing is, you're just trying to protect yourself with other things. If you use this global command, just be careful, because if a trunk dynamically gets created, your port fast goes away. Okay?
Okay.
But that's kind of why we prefer this configuration right here over the global configurations, if that makes sense. Okay? But anyway, that's port fast. Do you guys have any other kind of random thoughts about port fast or what it does, or any questions there? Don't do stupid things. Okay? That's my number one thing. And the stupid thing would be this. Let's say that your topology looks like this, okay? And you know that your root bridge is here, okay? If you do stupid things and you log on to access C here and you don't know what you're doing, so you go to this particular port and you say, you know what, I want to make this port fast. What's going to happen is the system's probably going to throw an error to say, hey, be careful, if you turn on port fast on any truncated ports, you're going to get temporary routing loops, because what's going to happen here is you're going to make this port transition from alternate blocking, okay? And you're going to transition this to designated forwarding. And if you're designated forwarding, this is then going to have a loop within this topology. So just be careful, right? I think when you do the port fast command on the per interface basis, it does give you a warning to not put port fast on any truncated links for this particular purpose. They don't want you to accidentally put port fast on an alternate blocking port, okay? Okay, so that's port fast. Are we okay with that so far? Let's talk about BPD card. What was that?
No, I tell you, sir, I was laughing because I've seen when the span tree takes down your whole network.
It could happen. I've seen it happen before, so I know it's possible. Okay, what's BPDU?
And that's where BPDU guard comes in.
Ah, very good. So BPDU guard is kind of like port fast, but in the way, what we do with BPDU guard is, again, we're not ever putting BPDU guard on these ports on any of our truncated ports, okay? These features are, again, for the ports that are connecting to our endpoints. So in BPDU guard, what's happening here is I prefer this configuration on the per interface basis as well. But the idea here is, if you make BPDU guard on this port, if this is an attacking PC, and let's say it's an attacking PC, or somebody brought a switch from home and then they plug it into the network, the idea with BPDU guard is it's meant to safeguard your switch topology the way that you set it. So even if somebody came over here and put in a switch here, okay, let's say this is a switch that they bought from Best Buy, they just wanted to increase their port density, right? So they plug into that switch that they bought. That switch could potentially, if they plug into this other port over here, what if this guy becomes the root bridge by accident, right? And that would change your entire traffic pattern for your switch topology. So BPDU guard is trying to safeguard your topology against rogue switches entering into the spanning tree topology is all, okay? Let me ask you guys, what happens when a switch sends a BPDU here and you receive a BPDU from a BPDU guard enabled port? What happens? I know somebody out there knows.
Error disabled.
Disable the port.
Very good. Error disabled. So you guys know. So that's the thing, is it will shut off that port, right? So you can do this either way. Honestly, I don't really care here. You could do access, you could do it on the interface, or you could do it on the global. If you do it on the global, this is going to be set for any port that is based on port fast. So any port that's port fast will automatically have this BPDU guard enabled. Okay, the way that I like to do it optimally is I like to put I like to put port fast on the per interface basis. Then I like to do the BPDU guard default command, because that will automatically apply to every port that's within port fast. Okay, so you can do it either way, but I prefer to use the less keystrokes possible, right, is probably the best way that I'd like to do it, right? BPDU filter, what is that doing? BPDU filters is just essentially disallowing BPDUs to be sent or received, but it doesn't actually do anything to the port. So the way that I've kind of conceptualized it to myself is that if I go over here, I make this BPDU filter, essentially what I'm doing is I'm turning off spanning tree. So you're turning off spanning tree, what is it, STP protocol. I'm turning off STP on that particular port, okay? So that port's not gonna be part of the spanning tree topology whatsoever, is what BPDU filter really does, okay? Because you're not sending or receiving BPDUs. Even if you receive BPDUs, it's not like you're getting error disabled or anything. Again, you're just turning off spanning tree on that particular port. Again, don't do BPDU filter on any of these ports up here for your, I guess, your topology ports, right? The ones that are connecting to your distribution or access level switches. Those ports should all be trusted ports, which you should not be putting any type of BPDU filter on those ports at all. Okay, this should only be done on endpoints only. All right. The stipulation, if you're going to be doing any of these BPDU guards or BPDU filters on a global, on the global command line, you just got to make sure that because you have that keyword port fast, those will only apply to ports that are within the port fast state. Okay?
I got a question.
This one's the only kind of like one that stands out from the list, because even though this is port fast, this gets applied to any port that's within the access state that's not trunking. Okay. Question.
I got a question.
Sure. Go ahead.
So why would you use BPDU filter for anything.
Again, just to turn off spanning tree if that's what you wanted to do. Again, I don't see it as often as I see these two, because I see port fasten BPU guard turned on most of the time for most people. If you use BPDU filter and you turn off spanning tree, that's as if you're not even doing these anyway, right? So that's the thing, is you're either using the top two or you're using BPDU filter and not port fasten BPU guard, right? It's either the top two or the bottom one. So that's what I've seen at least. Okay. So anyways, guys, I think that's it for our session. We did go a little bit over, but I hope you guys will forgive me. But hopefully you guys learned something new. Was it beneficial for you guys here, listening to the spanning tree stuff?
It's awesome.
Yeah, definitely. Thank you.
Okay. Do you guys want a copy of my slides here, or not really?
Yeah, that would be great. If I can get it.
Absolutely.
If you guys want a copy of those slides, send me an email. Let me, actually put in your emails inside of this Zoom session. And as soon as I see your emails, I'll go ahead and I'll email you guys out this PowerPoint, okay?
That'd be awesome. That'd be great.
Have a good one, guys. It was nice having you guys.
Thank you. Appreciate it.
Thanks a lot, man. Very good. All right.
For sure. I'll see you later.